As an example, let's look at the two-particle scattering. So we will assume that we have a particle with momentum p1, another particle with momentum p2, scattering into a particle with momentum k1 and another particle with momentum k2. Now to be specific, we will choose a reference frame in which we will be using the center of mass frame. So one particle is coming with momentum p1, the free momentum, which let's just call it p. The other particle will be coming in the opposite direction with momentum p2, which will be minus p since we are in the center of mass frame. Well, after the collision, one of them will move in one direction and the other one will be moving in the completely opposite direction. Let's say this is k1, which is k, and this is the k2 3 vector, which will be minus k, because we already used the momentum conservation. Now we will be studying the scattering of scalar particles. In particular, they don't have any spin. And so if you consider the rotational symmetry of the laws of nature, the only preferred directions here is this direction, the direction in which the initial particles are moving, and the direction in which the particles after the scattering are moving. So let's call this the angle between these two directions to be theta. So in this picture, it is this angle over here. This is our theta. Now, if you consider the rotational symmetry, for example, you can rotate our system. Let's just choose this axis to be our z-axis. This is our z-axis. We can rotate our system around the z-axis and nothing changes. So that basically tells us that nothing can depend on the angle around the z-axis. The physics will be the same, and hence our invariant matrix element, which contains all the dynamics of our system, can only be a function of theta itself. And of course, it will be also depend on the energy of our particles. But once we fix the energy of the initial particle, the energy of the final particles are also fixed. So this is the only variable that can change in the final state. Theta is the only parameter that can change in the final state. All the other parameters are fixed by the initial state. So we can actually, when we are calculating the sigma, let's write it out explicitly. This is d cubed k1 divided by 2 pi cube 2e1, d cubed k2 divided by 2 pi cube 2e2, and then we have the four-dimensional energy momentum conservation, p1 plus p2 minus k1 plus minus k2, and then we have the invariant matrix element squared and divided by the normalization and the flux of the incident particles, 2EA 2EB times VA minus VB. Now, using this Dirac delta over here, this 4 Dirac delta, we can evaluate the K2 integral. So this will become d cubed K1. Well, let me just call it K. As I have denoted over here, the three-dimensional K1 vector, I just call it K. Divided by 2 pi cube 2e1, 1 over 2 pi cube 2e2, and then we have a 2 pi to the 4 invariant matrix element squared divided by 2EA 2EB VA minus VB. Now I will be making some more simplifications. I will assume all particles to be have the same mass. that is m1 is equal to m2 is equal to m3 is equal to m4. I'm not yet assuming that my particles are identical. We will see what happens if we assume this final state particles to be identical. Now, if the masses are equal, keep in mind that the momenta of the incident particles, they also have the same magnitude, so their energies are the same. So EA and EB, they are the same. Furthermore, the energy of the final state particles, it will also be the same since they have the same momentum. And also keep in mind that after we take this d cubed k2 integral, then we have the k2 is equal to minus k, k1 is equal to k. So it is guaranteed by this Dirac delta. Without evaluating the k2 integral, there is no restriction on the value of k2. But after this Dirac delta integration, the 3 Dirac delta integration, I have the restriction that k2 plus k1 should be equal to p1 plus p2 in terms of 3 vectors. And there is, by the way, I took the 3 integrals. There is one more integral left, which will be Dirac delta of E1 plus E2 minus K1 minus Ek2. So I will also call E1 plus E2 the energy, sorry, this is EA, EB in the notation I used. So I will call EA plus EB to be E. And since EA plus EB, EA is equal to EB, and E1 is equal to E2, these are essentially because this is true because in the reference frame we are working with, P1 is equal to minus P2, or in terms of magnitudes, the magnitude of P1 is equal to P2, and after this K2 integral, we know that K1, the magnitude of the K1 3 vector is equal to the magnitude of the K2 3 vector. Now, I will call this EA plus EB to be E, which basically tells me that EA is equal to EB, which is equal to E over 2. And furthermore, E1 is equal to E2, so I will just use E1. Note that I don't yet know that I haven't yet imposed, since I didn't take this Dirac delta integral yet, I cannot really put everywhere E1 plus E2 is equal to E. Not yet. After the Dirac delta integral, we will have that. And furthermore, I will go to the spherical coordinates in terms of this d cubed k. So I will write d cubed k as k squared dk d omega. The omega is the direction of the scattered particle. So with these definitions, we can see that the sigma by d omega, the differential cross section, is equal to k squared dk. And let me cancel some Dirac delta. This cancels all of this and one of the 2 pi's over here. So it's k squared dk divided by 4 pi squared. Then I have 1 over 2e1 is just e. Similarly, 2e2 is also e. No, not e1. The 2ea is e, 2eb is e. So it's e squared. Well, let me keep VA minus VB for the time being. Then I have 1 over 4e1 squared. Since e1 and e2 they are equal, 2 makes 4e1 squared, and there is the m squared. And finally I have this, I still have that Dirac delta. Let me write it over here. 2e1 minus 2e2. 2e minus e. Now, since I have a Dirac delta, in fact, I can just replace E1 with E over 2 in everything that multiplies this Dirac delta. So I can even simplify it further. So it's k squared dk divided by 4 pi squared. Dirac delta, well, let me also write it as E1 minus E over 2 over 2e squared VA minus VB, and then here I have 4e1 squared is just e squared thanks to this Dirac delta. M squared. Now here e1, note that that is given by square root of k squared plus m squared, m being the common mass of all the particles. So here m1 is equal to m2 is equal to m3, m4. I call all of them m. So let's simplify it further. So here we have Dirac delta E1, which is square root of k squared plus m squared minus e over 2. So let's first identify what makes the argument of the Dirac delta 0. So the argument of the Dirac delta is 0 if k squared plus m squared is e squared over 4, or if k, the magnitude, remember this k is actually the magnitude of the 3 vector, not the 4 vector k, that k is equal to e squared over 4 minus m squared under the square root. So it has to be, keep in mind that this k, since it's the magnitude, it is positive. Now if we come back to this Dirac delta, let me just call this number k0. Square root of k squared plus m squared minus e over 2. This is actually equal to Dirac delta k minus k0 divided by the absolute value of the derivative with respect to k of square root of k squared plus m squared minus e over 2, evaluate that k is equal to k0. And that would give us, let's do the derivative, k minus k0 divided by k over square root of k squared plus m squared. I don't write the absolute value because this is already a positive quantity. So this is equal to Dirac delta k minus k0. Well, k squared plus m squared over here is already the EEK or E1, and E1 is, thanks to this Dirac delta, is just E over 2. So this is E over 2k, k0, and k0 is given over here, is this number over here. Let's also substitute that one. This is equal to Dirac delta of square E1 minus E over 2 is actually equal to Dirac delta k minus k0 E over E squared minus 4m squared under the square root. So now we can go back to our differential cross section. This was our differential cross section. So now if we use this expression of this Dirac delta over here, we have k squared dk divided by 8 pi squared e to the 4 1 over VA minus VB. There is m squared, and then this Dirac delta is Dirac delta k minus k0 e over e squared minus 4m squared times 1 over 4. And remember, k0 is e squared minus 4m squared under the square root divided by 2. So this, thanks to this Dirac delta, we can evaluate the k integral also, and the result just gives us a k. Instead of k, we will just put k0. This is e squared minus 4m squared divided by, here we have a 4, there is an 8, so it makes a 32 pi squared e to the 4 1 over va minus vb m squared. Well, this e cancels one of these e over here, so it's just e cubed. And we have another fact, square root of e squared minus 4m squared over here, so it gives a 1 over 2 over here. So the sigma over the omega is equal to this expression over here. Let's also simplify this va minus vb. Now, if you go back to our picture, you see here we have two particles having the same 3 momenta. They also have the same mass, so they have the same energy. So va and vb, in terms of their magnitude, they are equal, but just pointing in opposite directions. So if we go back, we have the va minus vb. This is equal to twice va. Now the v is twice p over e. The speed is just e, p momentum over e in our units. And this is equal to twice p, or p is e squared, e over 2 squared minus m squared over e. So the sigma over the omega will be equal to e squared minus 4m squared to the power 1/2 divided by 32 pi squared e cubed 1 over va minus vb. Now va minus vb we had already calculated. 1 over this number is e over 1 over 2 e squared minus 4m squared under the square root times m squared. So this e will cancel one of these, and this here we have this square root will cancel this square root, and we finally have the sigma over the omega is equal to 1 over 16 pi squared m squared over e squared. Now, usually in two particles scattering into two particles, the variables we use, here the omega is the solid angle in the center of mass frame. Rather than using these parameters, what we usually do is we define 3 parameters, S being the total momentum of the ingoing particles squared, T being the P1 minus K1 squared, and U being P2 minus K2 squared. So we define these variables, which are called Mandelstam variables. And we express everything in terms of these variables. So in the reference frame, well, let me replot the picture we have. So this is P1, which is P. This is P2, which is minus P. After the collision, this is K1, which we called K. And this is K2, which we called minus K. So, so the 4 vector P1 is E over 2, this is E1, and the 3 vector P. P2 is E over 2, and the 3 vector minus P. K1 is E over 2 K, and K2 is E over 2 minus K. So if you calculate S, which is P1 plus P2 squared, well, the P1 plus P2 for vector is E0 squared. This is just E squared. So wherever we see E, we can just replace it with square root of S. If we look at T, this is P1 minus K1 squared. P1 is over here, K1 is over here, so if we just take the difference, this is 0. P minus K squared, or minus P minus K 3 vector squared. If you take the squared, this will be minus P squared minus K squared plus 2P dot K. Note that since the energy of these particles are the same, P1 and K1, and their masses are the same, the magnitudes of P and K, they are also equal. So the magnitude of P is equal to the magnitude of K. Let's just call it P. So this T becomes P squared, 2P squared, cosine theta minus 1. Note that this angle over here is what we call theta. So theta is the angle between the vector P and the vector K. So this P dot K over here is actually their magnitudes multiplied, multiplication product of their magnitudes multiplied by cosine theta. So in particular, we can extract cosine theta here. We can write cosine theta as 1 plus T over 2P squared, which is 1 plus T over 2P squared. This is the 3 vector squared, is energy squared, which is E squared over 4 minus M squared, or 1 plus 2T over E squared minus 4M squared. This is our cosine theta. In fact, this is enough for us to express the cross section. Now, if we continue, if we just go back to our cross section expression, now d omega is v cosine theta multiplied by d phi. Nothing depends on phi. M depends only on theta, not on phi. So we can, neither E also doesn't depend on theta, it just depends on phi. So we can just integrate over phi, and this would just give us 2 pi d cosine theta. Now we had already calculated what cosine theta is. Cosine theta is given by this expression. So d cosine theta is 2 dt divided by E squared minus 4M squared. So this is 4 pi divided by E squared minus 4M squared dt. This is our d omega. So if you put this d omega into this expression over here, we will get d sigma over dt times E squared minus 4M squared over 4 pi. This is equal to 1 over 16 pi squared M squared over E squared, or this 4 pi cancels the 4 pi over here, d sigma over dt is equal to 1 over 4 pi M squared over E squared, remember, is S times S minus 4M squared. And this is our final expression for the scattering of two scalar particles. Now let's also discuss what happens if these scalar particles are identical. Remember the initial expression of the scattering cross section. we had this phase space over the final state particles. Now here essentially by carrying out these integrals we are summing over all distinct final states. But if the particles are identical, exchanging K1 and K2 doesn't give us a different state. It's basically the same state. So we should just we shouldn't count the exchanges of K1 and K2 as separate final states. But that means we need to just divide this d sigma by dt. Oops, sorry. For identical particles, this should be equal to 1 over 2 d sigma by dt for distinguishable final state of two particles. Now the two particles are distinguishable. If we had three of them, well, this is actually 2 factorial. If we had three of them, due to the different possible exchanges, if we had three identical particles, we should have divided by 3 factorial. Now, before closing this video, let me just check the 2 pi factors. So here we have the 2 pi to the 6th. There's just a 2 pi squared left. It's just 4 pi squared. And then we have 2e1 is just, and 2ea and 2eb. They're just factors of e. Eventually these also become e. So we have e to the 4. And this 2 is from the Dirac delta. And 2k0, and since k0 is square root of e squared over 4 minus m squared, this is 1 over 2, e squared minus m squared to the power 1 over 2. 2k0 is just e squared minus 4m squared. So here we have 4 pi squared, still continue, this is 8 pi squared. So is for here we have the k squared, and which becomes k0 squared, so there is an additional factor 4, it becomes 32 pi squared. And finally we have from VA minus VB another factor of 1 over 2. So this is equal to square e squared minus 4m squared to the 1 over 2 divided by 2e. So okay, these factors are also correct. Okay, this is our correct expression. We didn't miss, we don't seem to have missed any factors. And that is the end of this video.